so far we've only been talking about the standard conditions. So activity of ions 1, the pressure of any gases presence 1 bar, the pH is 0, temperature 25 degrees to 198 kelvins. What happens with the cell potential outside the standard conditions? Well, to calculate that, we need to use the Nernst equation, which relates the standard electropotential of a particular cell with the equilibrium constant. So you've got this fragment, this part of the equation that tells you information about, the conditions of that particular cell. The temperature that needs to be in Kelvin, R is the ideal gas constant in joules per Kelvin per mole, Z is the number of electrons transferred in the reaction, and F is Faraday's constant. Using the Nernst equation, we can work out electropotentials of a particular cell or a half cell at any conditions, pH, concentration, etc. So for example, let's look at this reaction, the reaction of permanganate anion to produce manganese 2 ions, and which has this particular standard electropotential 1.49. So I'm going to ask you to use the Nernst equation to calculate what would be the electron potential of that half cell, but outside the standard conditions, at a pH of 2.5, and with this particular ratio of concentration of manganese to permanganate anion, 1 to 100. So look at the Nernst equation and substitute the values, the quantities I'm giving you, and see if you can come up with an answer for the electropotential of this cell, this half reaction, this half cell, in these particular conditions. Stop the video now. So how would I go about solving this problem? Okay, well, I need to write the Nernst equation and substitute the values I know. I've got the electropotential for the half cell, which the problem already gives me, 1.49 volts. Then the rest are constants or information from the problem, and the log of would be the equilibrium constant, or in this case it's not at equilibrium, but the equilibrium quotient. So how would it be? Well, it would be the concentration of manganese 2 plus, because this is an electric redox process. We don't look about neutral species, only an ion, so I don't put the water. And in the denominator, I've got the concentration of manganese permanganate anion times the concentration of the hydrogen ions to the power of 8 because of the coefficient. And now I can substitute values. I've got the standard electropotential of the cell, which is 1.49. R is a constant, 8.31. The temperature doesn't specify, so I'm going to assume is room temperature 298 kelvins. The number of electrons exchanged is, in this half reaction, is 5. And F is the Faraday's constant, so it's a tabulated value, 96,485. Now, it tells me that the ratio manganese 2 plus to permanganate anion is 1 to 100, so I write 1 to 100. And the concentration of hydrogen ions, well, it tells me that the pH of the solution is 2.5. So the concentration of hydrogen ions would be 10 to the minus 2.5 and to the power of 8 because of the coefficient. So now I've got all the values that I need to solve this problem and come up with an answer. So in this way, you can work out at any conditions of temperature or pH or concentration of the ionic species in your reaction, what's going to be the electrode potential of the cell in those particular conditions. We can use the Nernst equation, and you can use the non-standard conditions to tune the reducing or oxidizing power of a particular element. For example, this example is the half reaction, the reduction of silver ions to silver. And this would be the Nernst equation applied to this particular reaction. And the electrode potential in standard conditions is 0.8 volts. If you have an additional reaction that removes silver ions from the medium, so remove silver ions from the medium, for example, by precipitating with chloride, then with the presence of chloride anion, you can precipitate silver chloride. Then this, you make this concentration of silver smaller, you make this value larger, and then the electrode potential of this half cell in those particular conditions with a process that removes ions from the medium, silver ions from the medium, is different, and this is reflected in this particular example. Instead of silver, you're using silver ions. You use silver ions in the form of silver chloride. The electrode potential of that particular half cell is smaller than if you were using silver ions dissolved but without the presence of chloride anions in the same medium. This is another example of how you can use additional processes surrounding those ions are intervening in that particular cell, or in this case a half cell, and complex formation or precipitation reactions affect the potential of that half reaction. So for example, we've got here the reduction of manganese 3 to manganese 2, and it has a particular electrode potential. And if you write the Nernst equation for this particular pair, manganese 3 to manganese 2, if instead of having a pH 0 in acidic pH in standard conditions, we use a basic pH, for example, the presence of sodium hydroxide, both metals precipitate as hydroxides in basic pH, but manganese 3 is more more affected by precipitation than manganese 2. So when you look at the potential of the reaction of manganese 3 hydroxide to manganese 2 hydroxide, although the exchange of electrons is the same, the electrode potential of that particular pair is different. As you can see, is much smaller. So with the Nernst equation, and playing with the different solubilities and stability and the ability of the different ions involved in those reactions to form complexes or precipitate, we can tune those electrode potentials to different values. And the Nernst equation allows us to predict what sort of effects those additional reactions have in the electrode potential of that particular pair. Typically, metals in higher oxidation states are more stable with respect to reduction in a basic pH than in an acidic pH. Typically, hydroxides of the higher oxidation states are less soluble than the hydroxides on the lower oxidation state, a bit like what we saw with manganese 3 and manganese 2. Manganese 3 hydroxide was less soluble than manganese 2 hydroxide. And when instead of a precipitate, where you're making it a complex, like with chlorides or ammonia, etc., the behavior is in general similar. The higher oxidation state will be more stabilized by complexation for the same ligand and metals and the same metal in two different oxidation states. The higher oxidation state will be more stabilized by complexation than the lower oxidation state.